Okay, hello all. Welcome to BVLSI session 3 online interactive session. So we will discuss today topic such as sequential logic circuits. We will understand the difference between sequential and combinational logic. Next we'll see the difference between a latch and a flip-flop whose CMOS implementation we will be seeing today. Next we'll see the concept of a CMOS bi-stable circuit. And after learning a bi-stable circuit, we will move on to CMOS SR latch. We'll first study it with an NOR base latch, and then we will study the same using NAND base SR latch. So let us begin with the very first topic. A combinational circuit or a non-regenerative circuit doesn't depend upon any previous inputs. It has a set of inputs and a fixed set of outputs. Here, at the output, at any instant of time, will depend only on the signal present at its inputs. So this is a combinational logic. Example of a combinational logic, you can consider it as a NAND gate. Any gate for that matter, a NAND gate. A NAND gate will produce the outputs only with respect to the two inputs, A and B. Let's say if A and B is 0, 0 or 0, 1 or 1, 0 or 1, 1, it will produce a unique combination of outputs only depending upon the present inputs. Whereas in contrast to this, a sequential circuit, the output depends upon the current input data along with the previous state of inputs. Then it is called as a regenerative circuits. So here the output, one of the outputs or few of the outputs goes back to the inputs and join with the present inputs, and then it produces the output. So it has a memory element along with it. So these states written over here is actually a memory element. So basically example of a sequential logic circuit will be memory elements such as latches, flip-flops, registers. Next we will see the types of sequential circuits. Broadly classified, they are classified into three types: bistable circuits, monostable circuits, and astable circuits. Already we know from the literature, bistable means two stable states, monostable has a single stable state, and astable has no stable state. Out of all these three, bistable circuits are most widely used. They are an important class of sequential circuits. So all your basic latches, flip-flop circuits, registers, all the memory elements used in your digital system design fall into category of your bistable circuits. Well, the example of a monostable circuit will be a monostable multivibrator. An example of a astable circuit will be a ring oscillator. Let us move on to the next topic. We'll now understand the difference between a latch and a flip-flop. Well, what is a latch? It is a level sensitive memory element that samples or evaluates the data on one phase of the clock and holds the data on the other phase. So basically a latch is a level triggered circuit. So let us understand what do you mean by level triggering. If you have a level sensitive clock over here, a high level triggering means the circuit will be active only when a high level is encountered. Similarly, a low level triggering means a circuit will be active and responding only when a low level of the clock is met. So hence it is called as a level triggering. And all the latches are level triggered latch. Next we'll see what is a flip-flop. A flip-flop or a register samples or evaluates the data on the rising or the falling edge of the clock pulse. For example, we can say if this is my clock pulse during all the rising edges, the circuit will be active. So this category is called as rising or a positive edge triggering. Similarly, when the circuit reacts or responds only to the negative edges of the clock pulses, it is called as falling edge triggered or negative edge triggered. So all the flip-flops are edge triggered. Now we move on to the next topic, bistable element. So everyone concentrate on this a simple inverter. This is a NOT gate. This is, I think that it is not so clear. This is my V in 1. This is my V out 1. This is my V in 2. And this is my V out 2 over here. This is my first NOT gate, second NOT gate. If I connect my output of the first NOT gate back to the input of the second NOT gate and the output of the second NOT gate back to the input of the first NOT gate, I have something called as cross coupled inverter circuit. So basically it is a bistable circuit, meaning it has two stable states. So let us look at this VTC curve. This is your normal VTC plot which we have plotted for other inverters. In this, you can see there are two states which are stable over here. One is over here, one is over here. That is either it is a VDD or it is a zero. In between, you can see a unstable state. That is the reason where all the transistors in the circuit are working in the saturation region. So we don't really know in that particular region, it's an unstable state. So if a circuit is initially operating at one of the stable states, it will preserve that state. So as you can see from the energy analogy, these two states are stable, whereas this state is unstable. Let us look into further details. Let us look at an analogy over here. This metastable, or it is also called as unstable state. So we have a ball and a hill analogy. As you can see, the balls over here and here are resting over a stable state, whereas ball over here on the top of the hill is in metastable or unstable state. A slight disturbance from here can push the ball towards the left or towards the right. Hence, it is a unstable state or a metastable state. Let us look into the circuit details of CMOS bi-stable circuit. So as we have earlier seen, it is a two cross-coupled CMOS inverters is nothing but a bi-stable circuit having two stable states. So V in of first inverter is connected to the V out of the second inverter, and V out of the first inverter is connected back to the input of the second inverter. So it's a closed loop. If we want to implement in the CMOS inverter form, so this is my inverter number 1 and this is my inverter number 2, and they are cross coupled like this. That is, the output of the first inverter is connected back to the input of the second inverter, and the input of the first inverter is connected to the output of the second inverter. So this is my CMOS bi-stable circuit. I'll give you 5 seconds to have a look at the diagram. Okay, we will proceed ahead. So here is a summary of whatever we have discussed. CMOS bi-stable circuit, it has two stable states or modes. So the circuit will preserve its states. The circuit will preserve its states as long as the power supply is on. Hence, it can perform a simple memory function of holding its state. The only limitation of this circuit, of this bi-stable circuit, is it has no provision for allowing its state to change externally from one stable state to another. That means there is no provision in the circuit. Once the state is fixed, there is no provision to change it externally whatsoever in this case. So this is an example of a CMOS bi-stable state. Let us look into another case. the remedy of this. So before that, we will see next a LT spice simulation of the same. So let us look into it. We will simulate a CMOS bi-stable circuit. So this is my CMOS inverter 1, CMOS inverter 2, and they are crossly coupled like this. Output of the first is connected input to the second, and the output of the second is connected back to the input of the first. So this is my CMOS bi-stable circuit, cross coupled inverter. So let us check the output of this. So we simulate this. We create two plot planes to plot the input and output. First, we will plot the input one, which is basically a pulse, and let us observe whether it's behaving as in yes, that's it. So it's a perfect inverter. So V in one, V out one, which will basically go to the input and output of the second inverter also. So this circuit over here is producing an inverted action, but there are only two stable states. Either the output is at 5 volts, logic 1, or the output is at 0 volts, logic 0. So this was the concept of CMOS bi-stable circuit or a cross-coupled inverter. Let us go back to our topic. So the remedy of this limitation over here, that is allowing the state to be changed externally, can be solved using this. Let us see that. So to allow a state of change, we can add simple switches to bistable circuit, which forces or triggers the circuit from one state to another. Well, the meaning of the statement is, we will see it in the next circuit, that is SR latch. In SR latch, as you might be knowing, S and R are the two external inputs. So basically what we are trying to say over here is, those simple switches which we add to the bistable circuit are S and R only. So our next topic of discussion will be CMOS SR latch circuit. First we will tackle it with NOR based approach. Second approach will be a NAND based approach of CMOS SR latch. So let us first look at NOR based SR latch. I request you all to kindly note down the truth table for your better understanding. So let us look at this functionality of this NOR based SR latch. First, we will try to analyze the working of this SR latch using gate level schematic. Again, I repeat, in the course of BVLSI, gate level schematic carries absolutely no marks. It is just drawn for a reference so that we can get the output expressions from here. So let us see the truth table over here. We have four combinations of SNR. We have two inputs. These are the two external inputs. And this is basically my cross-coupled inverter. So basically here I have used two NOR gates, NOR gate number 1, NOR gate number 2, and it has two complementary outputs, which is Q and Q bar. In the truth table, there is a term called as Qn plus 1. It indicates the next state. So the previous state will be Qn. I hope you are following. Similarly, the complemented output Qn plus 1 bar is my next state, whereas my previous state is Qn bar. So let us check the functionality of this circuit first. Whenever S is 1, S is logic 1, and R is 0, my Q n plus 1 is 1, and my Q bar will be 0. As you can see, Q and Q bar are always complementary. So let us check the functionality over here. I will show you the truth table of the NOR gate. So in a NOR gate, whenever both the inputs are 0, only then the output is 1. Rest all the cases, the output is 0. So in this case, if my Q is 1, let us check the second combination. So if my Q is 1, my Q goes here and my S is also 1. So what is my output of this Q bar? The Q bar becomes 0. Now Q bar becomes 0 will go over here and my R is also 0. So when it is 0, 0, I'll get Q as 1. So hence I get Q as 1 over here. This condition is called as set condition in a SR flip-flop. Similarly, when S is 0 and R is 1, when S is 0 over here and R is 1, let us consider Q as 0. So if Q is 0 over here, S is also 0, Q bar becomes 1. And when Q bar becomes 1, this goes over here, R is 1. So my output becomes Q bar becomes 1 and my Q becomes 0. So this is called as reset condition of the SR latch. Similarly, when S and R are 0, 0, both logic 0, my output will be the previous, whatever is my previous input. So based on that, it will depend. So this will become Qn, the previous output state, and this will become Qn bar. So actually it will hold the previous state. So once the input terminals of each NOR gate is used to cross couple the output of other NOR gate, yeah, this is the one of the input, and the second input terminal enables the triggering of the circuit. Just hold on a sec. Okay, so let us go back to the explanation of the circuit. So we have already seen the operation of it, but we'll see a special condition wherein S and R both are 1, 1. When S and R both are 1, 1, we know this has to be a complementary. So let us consider Q as 0. So if this is 0,
Sir, mute
when
all the
S and R
participants.
when SNR is 1 and 1, my output Q, let's consider it to be 0. So this is 1, this is 0. So my Q bar will be 0. And whenever my Q bar is 0 over here, irrespective of R, this also becomes 0. So basically, in this special condition, Q and Q bar are becoming both 0 at the same time, which is violating a complementary working of the SR latch. So basically, this operation, this state of my SR latch is called as not allowed or forbidden state. So let us go to the description of this. So you can have a look at the operation just now we have discussed. So this is my, yeah, so this is my SR latch and that's the operation of it. SR latch is in set condition when output Q is logic 1, Q bar is 0, regardless of the previous held state. SR latch is in reset condition when Q is 0 and Q bar is 1, regardless of the previously held state. SR is in hold condition when S and R, both the external inputs, are logic 0. So in this case, the SR latch will act as a CMOS bi-stable circuit, which we have seen previously. Also in the hold state, the SR latch will hold or preserve either one of its two stable state as determined by the previous inputs. So we said we shall see this in the simulation. And the fourth condition says when SNR is logic 0, the output of SR latch is not allowed. Now let us move on Now let us move on to the CMOS implementation of my above SR latch, which is NOR based. Now basically here one word is written, asynchronous sequential circuit. So we are implementing SR latch using static CMOS style using NOR based approach. So this is my cross coupled inverter. S and R are my two inputs. Q and Q bar are my two outputs. Basically it's a NOR gate. So in a NOR gate, my output is basically here in this case, Q bar is basically S is one of the inputs and the other input is coming from Q. So basically the equation over here is S plus Q the whole bar. Similarly, my Q output over here depends upon R and the second input is coming from Q bar. So basically it is NOR operation says it will be R plus Q bar the whole bar. In LT Spice, we don't have provision to write bar. So we write here the word Q bar. So basically Q bar will be S plus Q the whole bar and the output Q will be R plus Q bar the whole bar. The meaning of the word asynchronous means the outputs are not synchronous with respect to clock.
May I have your attention, please? Will the real Slim Shady please stand up?
Okay, next time we will see, after this is over, we will refer to synchronous sequential circuits. In that, we'll have a look at what do you mean by sequential circuits using synchronous approach. So we will study synchronous sequential circuits next time, which is actually a clocked based SR latch. So here absence of a clock means asynchronous. So this is my gate level schematic. So we have to implement SR latch using these equations, that is Q bar and Q. So we have already done many examples based on CMOS static style. So if we want to implement this directly, so first we will start with NMOS transistors. So here S plus Q. So my two NMOS transistors will be in parallel. Similarly, in my pull-up network, the two inputs, the two PMOS transistors will be in series.
I repeat, will the real Slim Shady please stand up? We're gonna have a problem here. Y'all act like you've never seen a white person before. Y'all.
Okay, wait a sec. Okay, fine. So this is my CMOS SR latch, NOR based design. Let me just expand it a little. Yeah. So first we will implement this Q bar. So Q bar says S plus Q the whole bar. So as I have said, S and Q has to be implemented with parallel NMOS transistors. And if two NMOSs are in parallel, this consists of a pull down network. My pull up network will be exactly complementary. That means my PMOS transistors will be in series. So my two inputs over here are S and Q bar. S and Q, sorry, S and Q. So this is my S and this is my Q over here. Similarly, my and my output is Q bar. Obviously, my output is Q bar. Similarly, if I check my second equation, that is Q is equal to R plus Q bar the whole bar, then my output over here is Q. My two inputs are here R and Q bar. You can see over here, this is my Q bar and this over here is my R. And why the two transistors are in parallel? Because here there is a plus sign. So a pull down network will consist of two parallel transistors over here, NMOS transistors. Similarly, my pull up network will be exactly complement of this pull down network. So two transistors will be in series, which are the PMOS transistors, also having the same inputs R and Q bar. And this is my cross coupled structure. So I'll give you around 5 to 10 seconds to note down the circuit. Y'all can take a print screen of this and note it down later for your understanding. Okay, so we shall proceed ahead. We will have to verify the truth table for this, whether this really works as a CMOS latch circuit or no. Basically, what we need to do over here is we have to determine whether all this, there are around total 1, 2, 3, 4, 4 over here and 4 over here. There are total 8 transistors, out of which 4 of them are NMOS transistors and remaining 4 are PMOS transistors. So we have to determine whether these transistors are on or off based on our inputs and dynamic outputs. So I'll just keep this open. I'll keep another window. Okay. Now basically we have to understand the working. I'll keep the truth table over here, but you all are free to establish this on your own. I hope it will be visible to all of you, the circuit diagram as well as the, yeah, I think it is clear now. So let us check the, here in this case, remember 1-1 combination is not checked because the output is not allowed. So I've only checked the 3 combinations over here. When S is 1, R is 0, that is Q is 1, Q bar is 0. When S is 0, R is 1, Q is 0, Q bar is 1. We have to verify and validate these results by the operation of my all 8 transistors. So when S and R are 0, 0, you might be wondering why there are 2 cases over here. Well, Q can be 1 or 0. Hence, there are 2 cases. In the first case over here, I have considered Q as 1, the previous state as Q as 1 and 0. And in the next case, I have considered it to be 0 and 1. So let us check the first condition over here. Let us concentrate in this and we can similarly explain the other condition. So let us check this first condition over here. When S is 1 and R is 0, let us see really whether my Q is 1 and Q bar is 0 coming or no. So let us go back to a circuit. If my S is 1 over here, so this one logic 1 goes to this transistor. So if you apply logic 1 to a NMOS transistor, this turns on. And if you apply logic 1 to a PMOS transistor, it just turns off. So my M1 is on and my M5 is off. So my M1 is on, M5 is off. Similarly, my R is 0. Whenever you apply logic 0 to NMOS transistor, this is off. And whenever you apply logic 0 to a PMOS transistor, this is on. So my M7 is on and my M4 is off. So my M7 is on, M4 is off. Similarly, let us check one of the condition. Let us assume that Q is 1 right now. If Q is 1 over here, Q is 1, Q is over here. So if it is logic 1, M6 is off and M2 is on. So M2 is on, M6 is off, right? If Q is 1, Q bar will be 0. So if Q bar is 0, this M8 will be 0 and M3 will be off. So M8 will be on and my M3 will be off. So here I have written here M3 is off, M8 is on. So I repeat it again. In this operation, M1 transistor is on, M2 transistor is on, which will pull the Q bar to ground. So basically Q bar becomes ground. Here in this case, M7 transistor is on and M8 transistor, M7 transistor is on, well M8 transistor is also on. So Q will be pulled up towards VDD. So indeed, my Q is indeed logic 1 and my Q bar is indeed logic 0. So hence my SR latch is in set condition. Similarly, you all can check it one by one and verify the other cases. I'll give you around 10 seconds to have a look over it. Okay, I hope you all have checked the other conditions. So due to limitation of time, we have to move forward and check the LT spice simulation of the circuit. So let us go and check that. Okay, so here I open up my LT spice window and I run my SR NOR based latch. So I'll just minimize this to show you the. So this is just now we have seen. I'll just show you the CMOS implementation of the circuit so that you can have a, you know, look over it. So this is my SO. What happened over here? Yeah. Let me just reduce the size of this window so that it fits over here. Yeah. Now it's fine. So as you can see, we can compare it side by side. I have my S over here, S over here. As you can see, have a look over it. Basically, it's exactly the same. Attempt has been made to keep the circuit as symmetric as possible. Meaning, whenever I do it on the paper, if I do the same thing on LT Spice simulation, you will have a good feel over it, the functionality over it. So these are my 4 PMOS transistors, and these 4 are my NMOS transistors. So I have my input as S, R, and my 2 complementary outputs Q and Q bar. So let us go ahead and as I've already shown you the LT Spice circuit simulation schematic part, now we'll go ahead and check the output. Basically going ahead and check the output meaning we have to verify the truth table. So basically we have to create 4 windows, one for S, R, and the remaining 2 for Q and Q bar. So let me just minimize the screen and plot those plots one by one. So I have my Q. Let us not plot Q first. Let us plot S first. So I have my S input over here, which is a clock, which is a pulse, continuous R, which are non-overlapping. These are my inputs. Always the non-overlapping condition should be satisfied. Now let us check the condition for Q. And similarly, Q bar. So I have my, let me change the color of this so that it becomes more visible to you all. Okay. So these are my inputs and outputs of SR latch, which is a proof. We will see it shortly whether it is really giving you a NOR based SR latch functionality or no. Just a moment. Let me just minimize this and open up the. Okay, yeah. So we will minimize this and we'll open the table. So to check the functionality over here. Okay. I hope it is clear to you all, the table. Okay. So let us check the first condition over here. The first condition over here is S is 0 and R is 1. So whenever S is 0 and R is 1, my Q is 0 and Q bar is 1. So let us check that. My S is 0, R is 1, Q is 0 and Q bar is 1. So there it is. One of the conditions is validated now. Let us go back to the second condition. Hello. Yeah. Thank you. Sorry, the net got disconnected. I'll continue. There is a request from someone. Yeah, okay, fine. So we can continue from here. So we were simulating LT Spice based SR latch using
Yes, sir.
using extremely sorry, there are some fluctuations in the internet. So I hope everyone is back.
Yes.
So let us go back to the functionality. We were verifying on the verge of verifying the truth table. So let us start again. SS0 RS1. So SS0 over here RS1. My output is 0. Q is 0 and Q bar is 1. Logic 1. So hence my functionality is proven over here. One condition. Next condition is S is 0 and R is also 0. So when S and R both are 0, it will hold on to the previous state. So previous state here was Q was 0 and Q bar was 1. So it will hold the previous condition. I hope it will clarify the work. Now let us check the third condition over here. When S is 1, R is 0. So when S is 1, R is 0, let us check what is the state of Q. Well, Q is 1 and Q bar is coming out to be 0. Yes, indeed, Q is 1 and Q bar is 0. And let us check the last condition. When S is 1, logic 1, and R is 1, what is my output state? My output state is forcibly Q and Q bar both are 0. So we have validated the results of a SR NOR base latch. So this circuit over here is indeed working as a NOR base SR latch. So we can have a look at the circuit functionality over here once. Always it's a good habit to write the total transistor count always. So just now we have seen the LT spice functionality of the circuit, and we have verified this indeed works as a CMOS SR latch NOR based design. I think we will stop over here. Meeting time is up. So in the next online interactive session, we will continue with the design of CMOS SR latch, but in this case we will see the NAND based design. So this will be our next topic. I will post about the timings of the session very soon. Thank you.